Happy Thursday morning. You guys are doing great so far this week. We are going to look at the same idea from yesterday, the idea of molarity, and we're going to discuss it a little bit more because it's so important. And so what you need to do is go to our Google site, or I guess you're here because you got the link. You need to open up your molarity and particle diagrams assignment, and I'm going to go through it with you until we get down to the molarity calculations. And you're going to use your understanding of molarity calculations from previous lessons to complete 1 through 6. So we're going to go through some of this explanation at the beginning, the first 4 explanation questions, and then you're going to do 1 through 6 by yourself or with your table mates. So let's get started. It says first that you need to draw a particle diagram for the 2 situations below. And so the first situation we already have written down on the board is solid sodium chloride. So what would the particle diagram look like? And so if we had a chunk of solid salt, it would look like this. We've got sodium particles or sodium atoms, just like this. And they're going to be connected to to chlorine atoms. And they'll all be laid out in this awesome crystal formation, or what scientists call a crystal lattice. Okay, and so you can see that every other one is a sodium or a chlorine, up and down and across. And this forms that crystal structure. So if you look really closely at a salt crystal, it's a crystal structure. And this is what it looks like in a particle diagram. We're also going to draw a particle diagram for water. And so what you'll draw is you'll have your oxygen in the middle with 2 hydrogens. And you'll have a bunch of those, but because it's a solution of water, they are going to be spread a little bit farther apart because they have more thermal energy than if it was a solid. And they could be moving around, so maybe I'll draw some swishies. And that's what you'll want to see when you're drawing a particle diagram for water. Okay, so we drew that, and now it's asking us if we took this solid salt, this chunk of salt, and we dropped it in there. We know from previous experiments that it's going to dissolve, but what is a dissociation equation, or an equation that shows that it's dissolving, look like? Well, let's write that down. So we start out, and I'll write over here, we start out with sodium chloride, solid, and it's going to dissociate or dissolve, and it's going to form sodium ions that are aqueous and chlorine ions that are aqueous. They're going to dissolve and break apart in the water and form individual ions that just float around dissociated. They're not associated with each other anymore. They're dissociated. And so that's going to be what our dissociation reaction looks like for changing solid sodium chloride into sodium ions and chlorine ions. That's what happens when you drop some salt into some water. So we're going to look down at this interesting idea, and it says energy must be absorbed to pull the ions away from each other. So we have to put energy in right here so that the ions can be pulled apart. Okay, because one's positive, one's negative, they're attracted to each other. So we have to add energy to be able to pull those apart. And the energy that's required right here, the energy required to break apart this crystal lattice, the energy required to break these molecules apart is called the lattice energy. Okay, and it comes from the energy that's in the water. Okay, we said there was some thermal energy in here. That energy is used to break the salt apart and dissociate it. Okay, that's the lattice energy. So my next question for you is, what would happen to the overall temperature of a solution as the absorbed ions are being pulled apart? is the temperature of the water going to drop or go up? Well, if lattice energy is required, it's pulling energy out of the water to break apart this ionic compound, the energy of the water is going to drop. So the thermal energy is going to go down. The temperature of the solution is going to go down. It's going to get colder because it's pulling energy out of the water to break apart those crystal structures. Okay, cool. So you circle decrease. So the next idea I want to discuss is really cool as well. In your notes it says, energy is released into solution when the water molecules surround the ions. So as soon as these molecules break apart, they're going to be surrounded by, I'm going to draw another beaker right here. Hopefully you can see that. We've got some sodium and some chlorine, some more chlorine, some more sodium, and obviously they're not the same amount, but they would be in reality. Now, the hydrogens have a positive charge, so they're going to be attracted to the chlorines, okay? So they're going to be attracted, they're going to surround those ions because those opposite charges are attracted. And the oxygens, because they're negatively charged, they're going to be attracted to the sodiums because sodium has a positive charge. And they're going to surround all the sodium ions. And what's happening there is energy is being released into solution. It's gaining more energy when the water molecules surround those ions. There's more energy being brought into solution. Okay, and so as the water molecules are attracted to and surround the ions, energy is released into the solution. Okay, so energy is being released here. We're gaining thermal energy. We're gaining something called temperature, and that energy that we're getting is called hydration energy. So as the water molecules surround the ions, we're gaining hydration energy, or energy as we hydrate these ions, okay, as we surround them with water. So my question for you is, what would happen to the overall temperature of this solution as we get hydration energy, or as hydration energy is released into the solution? Would the thermal energy go up or down? Yeah, the solution is going to increase in temperature because we're gaining energy. It's being released into the solution. It's absorbing energy. The solution is absorbing energy. So the temperature is going up. It's increasing. Okay, perfect. Now what we're going to do is we're going to look at lattice energy and hydration energy and compare and contrast and see how do they affect the solution. Okay, so first what we're going to do is we're going to draw a particle diagram for a 1 molar concentrated solution of sodium chloride and that's a 0.1 molar, and a 1.0 molar concentration solution of sodium chloride. Okay, so what would it look like? Well, we've got our water in here, and I'm just going to draw water like this because we know there's a bunch of particles of water in there. Now, 0.1 molar means there's 0.1 mole of salt per 1 liter of solution, of solvent, sorry. And so we're going to have a chlorine, 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 and we're going to have sodium, sodium, sodium. Now, what is changing here is this is 10 times more concentrated. So what I would have to do to make this accurate is draw, if I drew 3 chlorines and 3 sodiums, I'd have to draw 30 sodiums and 30 chlorines. So I better get started. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. And here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. This solution has way more salt dissolved in it with the same amount of water. They both have 1 liter of water, but this has 1 mole of sodium, and this only has 0.1 moles of sodium. And so this one is way more concentrated. Now, in the previous question, we looked at hydration energy, which is the energy that's added to solution as water surrounds the ions because they're attracted to each other, and lattice energy, which is the energy required to dissociate sodium and chlorine ions from the sodium chloride ionic compound. Now, the lattice energy drops the temperature because energy is required to break the bonds, and hydration energy increases the temperature because energy is added as the water and the sodium and the water and the chlorine are connected or are attracted to each other. And so this question is asking us to think a little bit about it. Now, how would you know when the lattice energy, so the energy required to break apart the crystal lattice, is greater than the hydration energy, which is the energy that's added so that when the water surrounds those ions? Because those two things are happening at the same time. They're happening simultaneously. So how would we know if the lattice energy is greater than the hydration energy? Well, because lattice energy decreases the temperature and hydration energy increases the temperature, this one's bigger, so the overall temperature change is going to be negative, or it's going to drop the overall temperature. That's how we would know that the lattice energy is greater than hydration energy. Okay, so we're going to actually practice some molarity calculations. You will definitely need to look at a periodic table to calculate the molar mass, because you're going to be converting, right, grams of some compound to moles of some compound. And then what you're going to do is you're going to divide it by the liters of the solvent. Okay, so make sure the units that you're using to dissolve in the volume are liters, not milliliters, because I know some people get tripped up on that. So jump into this. You have what it takes. You're just going to do a few, just 6 of them, and then you're done for today. You're awesome. Tomorrow we're going to have a cool lab that we're all going to do together, and some of the ingredients you might be able to find at home, so you might be able to do it at home while I'm going to do it, but I'm going to go into the lab, do an experiment, and you can use my data to complete the lab activity. Until next time, see you later.